We see two diagrams up on the board right now. What's the first one? Yep. It's a no. It's a converging mirror. We've got a converging mirror up here. What's another name for a converging mirror? Concave, right? Converging or concave mirror. Now, what's the bottom diagram that you see there? Yeah, Hamish? No. The bottom one is a lens, mirror lens. This one is a converging or convex lens. So you got to be careful here, right? The difference between converging and diverging for mirrors and lenses. Converging for mirrors is concave. Converging for lenses is convex.
How do you know the difference?
You got to remember the difference. Simple as that. You got to remember. Sorry, go ahead. No. It's if you know that this is a mirror, you have to know that this is a mirror. Like you got to be told that this is a mirror and that this is a lens. But if you're told that this is a mirror and that this is a lens, you got to remember that concave means thinner in the middle than it is at the edges. Whether it's drawn like this, that's flat, or whether it's drawn like this, doesn't really matter. If it's thinner in the middle than it is at the edges, it's concave. If it's concave, then it's got to be converging. Now for lenses, if it's thicker in the middle, then it's convex, and if it's convex, then it's got to be converging. Chibo? Okay. Now, what I want to do here is draw the connection between these two optical devices here, the converging mirror and the converging lens. I want to put an object right here in the converging mirror, same place as I have it for the converging lens. And I'm going to draw the ray diagram for both of these. For the mirror, and this is what we did yesterday, we draw two rays. There's three that we can draw, but two that we ever need to draw. The first ray is going to go parallel to the principal axis from the top of the object. Then it's going to go down through the focal point. The second ray is going to go down through the focal point, and then it's going to go parallel to the principal axis. We find in that case that we get an image that is, what are the characteristics of it? It's yeah, go ahead. Yeah, good. It's larger. It's inverted, good, and it is for real. That could be real or virtual. Yeah, you know what? We'll do that third one in a minute here, okay? We don't need to draw the third one for this ray diagram, so we won't bother. If we don't need to, we won't. Take the easy way out, right? For the next diagram that we draw, we will have to, though. For the next one that we draw on the next page, that is. Now, let's take a look at the bottom diagram. This is a converging lens or a convex lens. If we draw a ray diagram for this one, we're going to draw it with the first ray from the top of the object, then down through the focal point. Then we're going to draw the next one down through the optical center, and we're going to get an image that looks something like this. This image is larger, inverted, and real. In fact, you will always get, no matter which converging mirror you draw, you will always get the same image characteristics as the equivalent converging lens. If the object distance is between f and 2f, it doesn't matter whether you've got a converging mirror or you've got a converging lens, the same characteristics will appear. Let's just double check that though. Okay, let's just double check that with another ray diagram right here, where we're going to make our object inside the focal point of this mirror. This is where, Joshua, we're going to draw that third ray here, okay? First ray is still the same. It's going to be from the top of the object parallel to the principal axis, and then it's going to go down through the focal point. The second ray, we're not going to draw. It's the one that would normally go through the focal point and then parallel, but the focal point's behind me now, so I'm not going to draw that one. I'm going to draw the one that goes from the top of the object. This is my third ray. Top of the object, as if it's going away from 2F, or the center of curvature of this mirror. They don't intersect anywhere, so I'm going to extend those rays, the reflected portion of those rays, that is, back behind the mirror, and I'm going to find that it produces an image that is larger, upright, and it is virtual. We know it's virtual because dotted lines intersect. It means we can't project it onto the screen. Now, because we've got a converging lens below it and the object is placed in the same place, we should expect to get three characteristics that are exactly the same as the ones we just got for the mirror. So let's try it. We got a ray, goes from the top of the object parallel, then down through the focal point. We have one that goes down through the optical center. They don't converge, so we extend these back here. And when we do, what do we find? Well, the image is larger, upright, and virtual. Make sense? I'm going to give you a little out here. I shouldn't do this, but I'm going to anyways. If you don't feel comfortable drawing ray diagrams for one or the other, and typically if people have trouble, it would be for the mirrors, if people have trouble, then you can always cheat a little bit. Draw the ray diagram for the other one. If you've got a converging mirror with the object inside the focal length, and you just have so much trouble drawing that ray diagram, if you draw the ray diagram for the converging lens, you get the same characteristics. Does that make sense? The image is on the other side, right? It's on the opposite side, but you get the exact same characteristics. Now, what you got to be careful of is that you don't say, okay, I've got a concave mirror. Oh, I don't like that. Let me draw the image for a concave lens. That's not going to work, right? If I have a concave mirror that's converging, I need to draw if I want to draw a lens instead of the mirror, then I need to draw a convex lens, which is converging. All right, go ahead.
Just to make sure, the magnification on the bottom one.
No, the magnification on both of them would be considered positive because no, it has to be on the same side of the principal axis. So if they're both upright, M is positive up there. By that rationale, M is positive down here as well. Doesn't matter that one's on one side, one's on the other side of the device, the optical device. It makes no difference. Now, these are both going to be negative image distances, despite the fact that one's on the left, one's on the right, because they're both virtual images. They're both going to be positive DOs. They're both going to be positive Fs. Everything about them is going to be the same, except when you draw the diagram, one's on one side, one's on the other. But mathematically, attributes-wise, they're both exactly the same. Always, always. As long as you have converging and converging, or, as you're going to see in a second, diverging and diverging. Let's draw one that's diverging. Okay, here's a diverging mirror, here's a diverging lens. It doesn't really matter where we put our object because we know that we get the same characteristics regardless of where our object is when it's diverging. But let's just be consistent, put our object in between F and 2F up here for the mirror. First ray is going to go parallel to the principal axis. It's not going to go down here through the focal point. It's not going to go back here somewhere. Rather, it's going to diverge up here away from that focal point. Second ray is going to go down toward the focal point, but it never really makes it to the focal point because the mirror gets in the way. Rather, when it hits the mirror, it's going to reflect back like this. Let's extend that reflected ray, and we find that the image produced here is, what would it be? Smaller. It would be upright. And it would be virtual. Because we have a diverging mirror, and a diverging lens, and the object is placed at the same place, okay, in between F and 2F, we should expect to see the exact same characteristics for the lens. Let's try it. First ray, parallel, and then it diverges up away from the focal point. Second ray is going to go down through the optical center, and technically, we look at the extended portion of that ray. We see that two dotted lines intersect. What are the characteristics? It's smaller, upright, and it's virtual. Does that make sense? Okay, I'm not suggesting that you should never draw ray diagrams from mirrors. Okay, my preference would be draw the ray diagrams from mirrors when you have a situation involving mirrors. But if you just can't figure that out, and some people have some trouble with that because the rays are different, right? Here we've got ray 1 and ray 2. In this one, we've got ray 1 and ray 3. This one especially messes people up when you have to draw that third ray. Okay, if that just doesn't work for you, then draw the equivalent ray diagram for the lens because it will give you the same characteristics. All right? Now, we're going to talk about a little bit of mirror math here now, just as we talked about some lens math earlier on, yesterday. There are, just like for lenses, two equations that describe the mathematics of mirrors. And they are, in fact, the same two equations. 1 over f is equal to 1 over do plus 1 over di. We called that the thin lens equation yesterday. Today we're calling it the mirror equation. We also have the magnification equation for lenses. We're going to introduce the same equation for mirrors. M is equal to hi over ho equals negative di over do. F is focal length, the distance from the focal point to the mirror. Do is the distance from the object to the mirror. Di is the distance from the image to the mirror. M is how big the image is compared to the object. Hi is the height of the object. Ho is the height of the image. Other way around, sorry. Hi is the height of the image. Ho is the height of the object. Exactly the same as it was for lenses. Now, as I scroll down and fill in the table for sign conventions, it's once again exactly the same. I'm going to fill it in just as a little bit of a review, but you know the answers to this. You know how to fill in these blanks already. If we group F, DO, and DI together, when are they positive? They are positive if they are, somebody said it, real. Yeah, we're going to make F positive if it's a real focal point. And when do we have a real focal point? When it's a converging device. It doesn't matter whether it's converging lens or a converging mirror, the focal point will be positive. Now be careful. Again, converging lens is convex, converging mirror is concave. Okay, that's different. But it will always be positive if it's converging. And of course, it's going to be negative if it's diverging, because that produces a virtual focal point. DO is going to be positive if you have a real object. And for us in Physics 30, it's always going to be a real object. Next year, if you take physics, it won't necessarily be a real object. Sometimes you can get a virtual object, but in Physics 30, when you have just a one lens at a time, it has to be a real object. Therefore, it's got to be a positive DO. I'm just going to put a little line through there because technically it's negative when it's virtual, but that's not going to happen for us. DI is positive if you got a real image. And you got a real image in exactly the same situations as you had a real image for a converging or diverging lens. It's going to be negative if you have a virtual image. Same deal. The image is going to be virtual always if it's a diverging lens or a diverging mirror. And sometimes it's going to be negative or virtual if you have a converging lens or mirror. You got to look at each individual case there. Now my next grouping, the green grouping, was HO and HI. HO is positive if the object is upright, right side up. And so is HI. It's positive if you have an upright image. And of course, each of them are negative if they're inverted. And finally, the last one, the magnification. Nothing new here, right? This page is exactly the same as the page that we wrote down the other day for lenses. Nothing new. Okay, not going to change now. The magnification is the same as it was for lenses as well. M is going to be positive if the object and the image are both either upright or inverted. In other words, if they're on the same side of the principal axis. They're both either upright or inverted. If one of them is upright and one of them is inverted, then we're going to find it's a negative magnification. Listen, 99 times out of 100, the object is upright. So 99 times out of 100, you can look at the magnification, say if it's positive, well, then the image is just upright. If it's negative, then the image is inverted. So 99 times out of 100, we can follow the same convention for M as we do HO and HI. But that 1% of the time, when the object is upside down, well, then the image height might be a different sign than the magnification. All right, let's do an example. This one's on our textbook as well. Page 664, it says, an object is located 20 centimeters from a converging mirror. It's a converging mirror, which means that the focal length is is positive, which is good. We don't have to worry about sticking a negative in there. We just want to draw attention to it so that we don't forget down the road when we do have a diverging mirror, we don't forget to draw attention to that and make it a negative value. Where will the image form relative to the vertex of the mirror? In other words, how far away from the mirror is it? And if the object is 5 centimeters high, what's the attitude? The attitude means right side up or upside down. What's the height and the magnification of the image? We're going to say DO is 20 centimeters here. We're going to say the focal length is 15 centimeters here. DO is always positive. F is positive here because the mirror is converging. We want to find DI, where the image is going to be formed. We know the object height is 5 centimeters. We want to find the image height, and we want to find the magnification. So we got three unknowns. We're going to use both equations. Let's start with the mirror equation. 1 over F is equal to 1 over DO plus 1 over DI. We're going to say 1 over 15 is equal to 1 over 20 plus 1 over DI. We solve for DI here. We can do that by finding the common denominator, which in this case would be 60. Becomes 4 over 60 minus 3 over 60. Or the easier way to do it is just to take your calculator and use the little cheat, the non-cheating cheat. You're allowed to do it, right? Because it's on your calculator. It's a built-in function. We'll say 1 over 15 minus 1 over 20. Enter, and then let's flip that over. We get a value of 60. Should be 60.0, I guess, for the image distance. Now, we're not asked whether this is real or virtual, but we could determine that right now. Is it a real or virtual image? Right now, just by this number, real or virtual? It's real, because our image distance is positive. Again, we're not asked that, but we easily could have been asked whether it was real or virtual. All right, next thing, let's find the magnification. M is equal to negative DI over DO. That's going to be negative 60 over DO, which is 20. That gives me a magnification of negative 3. What's the attitude of this? Right side up or upside down? Magnification is negative, good. That means it's going to be upside down, inverted. Now, we're not asked for larger, smaller, same size, but we could identify that now. Is it larger, smaller, or same size? Magnification is 3. It must be, yeah, good. If the magnification is greater than 1, it's a larger image. Now, let's find the image height here. M is equal to HI over HO. Negative 3 equals HI over 20. No, HI over 5, I should say. There's the image height. Now, the image height could have also told me that it was inverted because it's a negative HI, and it also could have told me that it's larger because the object is only 5 centimeters tall and the image is 15. So either one of these gives me those last two characteristics. I got 5 questions for you on page 664 for you to work on. I'll leave these up on the board. You can also open it up on your phones. You're going to have the next 15-ish minutes to work on these questions. Get down what you can. Ask me questions as I'm walking around and make sure that it's good before we leave here today.